After studying this module, you shall be able to know about another model used for panel data estimation, that is random effects model, learn about the assumptions that are needed while using random effects model, identify the fixed and random effects model are apt to use, understand about the correlated random effects approach, learn about Hausman test. The fixed effects or least square dummy variable is very straightforward to apply, but this can be expensive in terms of degrees of freedom if we have several cross-sectional units. The proponents of error components model or ECM or random effects model suggest that if the dummy variables represent a lack of knowledge about the true model, then this ignorance should be expressed through the disturbance term. Random effects. Let the model be YIT beta 1i plus beta 2x2i plus beta 3x3i plus mu it. In this equation, instead of treating beta 1i as fixed, we assume that it is a random variable with a mean value of beta 1, no subscript I, and the intercept value for an individual company can be expressed as beta 1i is equal to beta 1 plus ai, I being 1 to n. Here ai is a random error term with a mean value of 0 and a variance of sigma square a. Substituting equation 2 into 1, we get the unobserved model. YIT is equal to beta naught plus beta 1 x1 it plus this equation will go on to beta k xk it plus ai plus mu it. This can be further represented as YIT is equal to beta naught plus beta 1 x1 it going till beta k xk it plus VIT, where VIT is equal to AI plus mu it is a composite error term. It includes two components, AI, which is the cross section or individual specific error component, and mu it, which is the combined time series and cross section error component. Note that AI is normally distributed with mean 0 and variance sigma square a. Mu it is normally distributed with mean 0 and variance sigma square mu. Expected value of AI and mu it is equal to 0, and expected value of AI aj is equal to 0, I not equal to j. That is, the individual error components are not correlated with each other and are not autocorrelated with both cross-section and time series units. The difference between fixed effects model and random effects model is that in fixed effects model, each cross-sectional unit has its own intercept value in all n such values for n cross-sectional units, whereas in random effect model, the intercept beta 1 represents the mean value of all the cross-sectional intercepts, and the error component AI represents the deviation of individual intercept from the mean value. AI is not directly observable. It is known as unobservable or latent variable. From assumptions stated above, it follows that the expectation of VIT is equal to 0 and the variance of VIT is equal to sigma square A plus sigma square mu, that is variance of A plus variance of mu. The above equation shows that the error term VIT is homoscedastic. However, it can be shown that VIT and VIS are correlated. That means the error term of a given cross-sectional unit at two different points in time are correlated. The correlation coefficient between VIT and VIS is equal to sigma square A divided by sigma square A plus sigma square U T not equal to S. In fixed effects of first differencing, we aim at eliminating unobserved effect because it is thought to be correlated with one or more of xjit. But on the contrary, when this unobserved effect is not correlated or uncorrelated with each explanatory variable in all time period, then using a transformation to eliminate AI will give inefficient estimators. In equation 7, for any cross-sectional unit, the value of the correlation between error terms at two different times remains same no matter how far apart the two time periods are. Moreover, the correlation structure remains the same for all cross-sectional units. That is, it is identical for all individuals. While estimating by ordinary least squares, this correlation structure should be taken into account, otherwise the resulting estimators will be inefficient. The appropriate method for this is generalized least square method. The ideal random effects assumption include all the fixed effects assumption plus the additional requirement that AI is independent of all explanatory variables in all time periods. The ideal random effects assumptions include the following. Number 1, for each I, the model is YIT is equal to beta naught plus beta 1 XIT till beta k xkit plus AI plus UIT, t going from 1 to capital T, where the beta j are the parameters to estimate and AI is the unobserved effect. Sample is drawn randomly from the cross section. That was the second assumption. Assumption number 3, for each t, the expected value of the idiosyncratic error given the explanatory variables in all time periods and unobserved effect is 0. That is, expectation of UIT given xi and AI is equal to 0. Number 4, variance of mu it given xi AI is equal to variance of mu it is equal to sigma square mu for all t going from 1 to capital T. Number 5, for all t not equal to s, the idiosyncratic errors are uncorrelated, conditional on all explanatory variables and AI. That is, covariance of mu it, mu is given xi AI is equal to 0. Number 6, conditional on xi and AI, the mu it are independent and identically distributed as normal with mean 0 and variance sigma square mu. Number 7, there are no perfect linear relationships among the explanatory variables. The cost of allowing time constant regressors is that we must add assumptions about how the unobserved effect AI is related to the explanatory variables. The expected value of AI given all explanatory variable is constant, that is AI given xi is equal to beta naught. That was the assumption number 8. This is the assumption that rules out correlation between the unobserved effect and the explanatory variables, and it is the key distinction between fixed effects and random effects. Because we are assuming the correlation between AI and all xit, we can add time constant explanatory variables. Assumption number 9, the variance of AI given all explanatory variables is constant. Variance AI given xi is equal to sigma square A. GLS transformation derivation. Deriving the GLS transformation that eliminates serial correlation in the errors requires sophisticated matrix algebra, but the transformation itself is simple. Define theta is equal to 1 minus under root sigma square mu divided by sigma square mu plus t into sigma square A, which is between 0 and 1. Then the transformed equation turns out to be YIT minus theta yi bar is equal to beta naught 1 minus theta plus beta 1 xit 1 minus theta xi bar 1 going till beta k xit k minus theta xi bar k plus vit minus theta vi, where the over bar again denotes the time averages. This is a very interesting equation as it involves quasi-demeaned data on each variable. The fixed effects estimator subtracts the time averages from the corresponding variable. The random effects transformation subtracts a fraction of that time average, where the fraction depends on sigma square u, sigma square A, and the number of time periods, T, capital T. The GLS estimator is simply the pooled OLS estimator of equation 9. It is hardly obvious that the errors in 9 are serially uncorrelated, but they are. The transformation in I allows for explanatory variables that are constant over time, and this is one advantage of random effects over either fixed effects or first differencing. This is possible because random effect assumes that the unobserved effect is uncorrelated with all explanatory variables. Whether the explanatory variables are fixed over time or not, thus in a wage equation we can include a variable such as education even if it does not change over time. But we are assuming that education is uncorrelated with AI, which contains ability and family background. In many applications, the whole reason for using panel data is to allow the unobserved effect to be correlated with the explanatory variables. There are several ways to estimate parameter theta, which may be based on pooled OLS, ordinary least squares, or fixed effects. For example, generally theta hat takes the form theta hat is equal to 1 minus under root 1 upon 1 plus t brackets sigma square a divided by sigma hat square u, where sigma hat square a is a consistent estimator of sigma square a and the sigma hat square mu is a consistent estimator of sigma square mu. These estimators can be based on the pooled OLS of fixed effects residuals. Many econometric packages support estimation of random effects model and automatically compute some version of theta hat. The feasible GLS estimator that uses theta hat in place of theta is called the random effects estimator. Under the assumptions of random effects, the estimator is consistent, not unbiased, and asymptotically distributed as n gets large with fixed capital T. The properties of random effects estimator with small n and large t are largely unknown, although it has certainly been used in such situations. Equation 9 allows us to relate the random effects estimator to both pooled OLS and fixed effects. Pooled OLS is obtained when theta is equal to 0 and fixed effects is obtained when theta is equal to 1. In practice, the estimate theta hat is never 0 or 1. But if theta hat is close to 0, the random effect estimates will be close to the pooled OLS estimates. This is the case when the unobserved effect AI is relatively unimportant because it has small variance relative to sigma square mu. It is more common for sigma square A to be large relative to sigma square mu, in which case theta hat will be closer to unity. As capital T gets large, theta hat tends to 1, and this makes the random effects and fixed effects estimates very similar. Fixed effects versus random effects. Because fixed effects allows arbitrary correlation between AI and XJIT, while random effects does not, fixed effect is widely thought to be a more convincing tool for estimating ceteris paribus effects. Still, random effects is applied in certain situations. If the key explanatory variable is constant over time, we cannot use fixed effects to estimate its effect on y. If t is large and n is small, there is likely to be little difference in the values of the parameters estimated by fixed effects model and random effects model. Hence, the choice here is based on computational convenience. On this score, fixed effects model may be preferable. If n is large and t is small, and if the assumptions underlying random effects model hold, random effects model estimators are more efficient than fixed effects model estimators. Typically, if one uses random effects, as many time constant controls as possible are included among the explanatory variables. Within fixed effect analysis, it is not necessary to include such controls. Random effect is preferred to pooled OLS because random effect is generally more efficient. If our interest is in a time varying explanatory variable, then use random effects, but only in the situations in which the covariance between XJIT and AI is equal to 0. Should be considered the exception rather than the rule. If the key policy variables are set experimentally, say each year children are randomly assigned to classes of different sizes, then random effects would be appropriate for estimating the effect of class size on performance. The correlated random effects approach. There exists an alternative to fixed effects that still allows AI to be correlated with the observed explanatory variable. To describe the approach, consider a model. YIT is equal to beta 1 xit plus AI plus mu it, t going from 1 to t. Rather than assume AI is correlated with xit, t going from 1 to t, which is random effects approach, or take away time averages to remove the fixed effects approach, we might instead model correlation between AI and xit, t going from 1 to capital T, because AI is constant over time by definition, allowing it to be correlated with the average level of the xit has certain appeal. Let xi bar is equal to sigma small t going from 1 to capital T xit divided by capital T be the time average. Assuming a simple linear model, AI is equal to alpha plus y xi bar plus Ri, where Ri is assumed to be uncorrelated with each xit. Because xi bar is a linear function of xit, covariance xi bar Ri is equal to 0. Both the above equations imply that AI and xi bar are correlated wherever gamma is not equal to 0. The correlated random effects, that is CRE approach, uses equation 11 in conjunction with equation 10. Substituting the former in the latter gives YIT is equal to beta xit plus alpha plus gamma xi bar plus Ri plus mu it. This reduces to alpha plus beta xit plus gamma xi bar plus Ri plus mu it. Alpha plus beta xit plus gamma xi bar plus Ri plus mu it. Interesting to note that equation 13, the above equation, still include a composite error term, Ri plus mu it, where Ri is time constant, unobservable, and mu it is idiosyncratic shocks. Importantly, the following assumption hold when we replace AI with Ri. Also, because mu it is assumed to be uncorrelated with xit, all S and T, mu it is also uncorrelated with xi bar. Covariance xit j with AI is equal to 0. T going from 1 to capital T, j going from 1 to k. All of these assumptions add up to random effects estimation of the equation. YIT is equal to alpha plus beta xit plus gamma xi bar plus Ri plus mu it, which is similar to usual random effects equation with important addition of the time average variable xi bar. It is the addition of xi bar that controls for the correlation between AI and the sequence xit, t going from 1 to capital T, and Ri is uncorrelated with xit. Estimation of equation 14 gives alpha hat, beta hat, and gamma hat. They are all correlated random effect estimators. It can be shown beta hat correlated random effect estimator is equal to beta hat fixed effect estimator. In other words, adding the time average xi bar and using random effects is the same as subtracting the time averages and using pooled OLS. Hausman test. It is still fairly common to see researchers apply both random effect and fixed effects and then formally test for statistically significant differences in the coefficients on the time varying explanatory variable. Hausman first proposed such a test, and some econometric packages routinely compute the Hausman test under the full set of random effects assumptions listed above. The idea is that one uses the random effects estimates unless the Hausman test rejects it. Covariance between xjit and AI is 0. In practice, a failure to reject means either that the random effect and fixed effect estimates are sufficiently close so that it does not matter which is used, or the sampling variation is so large in the fixed effect estimates that one cannot conclude practically significant differences are statistically significant. A rejection using the Hausman test is taken to mean that the key random effect assumption is false, and then the fixed effects estimates are used. A rejection using the Hausman test is taken to mean that the key random effect assumption is false, and then the fixed effect estimates are used. In other words, it compares the fixed effect and random effect models. If both fixed and random effect turn out to be significant, Hausman test will give you a good idea which one to choose. The null hypothesis is that fixed or random is not correlated with other regressors. A random effect model is better than the fixed effect model, and a random effect model is consistent, are not correct null hypothesis for the Hausman test. If the null hypothesis is rejected, a random effect model will be suffering from the violation of the Gauss-Markov theorem and end up with biased and inconsistent estimates. By contrast, a fixed effect model still remains unbiased and consistent. To make it simple, if the null hypothesis is rejected, use the fixed effect model. Otherwise, go for the random effect model. Summary. In this module, we have continued our discussion of panel data methods by studying another way of estimating panel data model, that is random effects. We have also briefly discussed correlated random effect approach. It allows one to incorporate time constant variables in an equation that delivers the fixed effect estimates of the time varying variables. We have seen that the random effects estimator is apt when the unobserved effect is thought to be uncorrelated with all the explanatory variables. Then AI can be left in the error term, and the resulting serial correlation over time can be handled by generalized least squares estimation. One advantage of random effect model over fixed effect model is that it is economical in degrees of freedom, as we do not have to estimate n cross-sectional intercepts. We need only to estimate the mean value of the intercept and its variance. Random effect model is appropriate in situations where the intercept of each cross-sectional unit is uncorrelated with the regressors. The Hausman test can be used to decide between fixed effects model and the random effects model. Despite its increasing popularity in applied research and despite increasing availability of such data, panel data regressions may not be appropriate in every situation. One has to use some practical judgment in each case.